Greetings. In this one we will talk about something called the angle of friction. So basically there is a particular angle at which, for example, if we have an inclined plane and there's a free body on it, some surface, and on this body there's friction between the two. Well, at some angles it will still kind of stay in place, and at some point it will start to slide down, and it depends on the coefficient of friction and also the angle in relation to it directly, by the way. What is that angle at which it will start to slide down? So let's talk about that. And first of all, I will give an example regarding a straight horizontal plane on which there's a free body, and this thing applies the same way kind of. And the most important points here will be the coefficient of friction that has to be included in this explanation. Also, there will be mentions of course, to this directly related normal force and horizontal force. And we will not draw everything. We're considering a static scenario. So yes, it is a moment where the object is barely still stationary and it's very close to starting to move. Such a very small amount of force will cause it to start moving, to get into motion. And so it is still a static scenario nevertheless. And therefore, some things should be assumed. In general, the y forces have to be together zero, cancel out each other. So if I'm talking about n force going up, there should be in that whole ridge for that whole body also some forces for it to stay in place. That has to be some opposing force. But I'm not drawing everything to save time and space. So keep that in mind. We're taking a look at the most important points of it. So let's start with this case. We have some, well, it's basically the same case and it's very general. So it's not really even needed to call it an example. Better to call it like an explanation or point of view basically on this context. So this is the free body, this rectangle, this is the surface, and between them there is some friction. And we're talking about static coefficient of friction, by the way. There's a different coefficient for friction for static scenarios and for kinematic scenarios, because when the object is already sliding along that surface, there's a usually lower coefficient of friction. So the ratio between the resistant force and the normal force caused, for example, by the free body being attached by gravity to the surface, the ratio should be lower when it's already in motion than when it's still not moving. So we're considering the coefficient, static coefficient of friction, which is, by the way, usually denoted mu sub s and as static for the index. And then we have this free body. And I'm considering two forces. So a normal force, and again, yes, this is caused by gravity perhaps, or something else. Most usually gravity in real case scenarios. And also if I'm, for example, considering the real world scenario of something inclined on a plane and now determining what is the angle at which it will start sliding down by itself. You know, what has to be the angle in relation, for example, to the material's coefficient of friction. So depending on the particular material, we will be able to determine, observe, or even calculate with some data what the angle will be when the thing starts sliding down by itself. So until what angle will it still kind of stay in place, and at what angle will it suddenly start sliding down. So that's the point. But regardless of that, now we have a force that's normal, that will be n, and then there's going to be another thing that's going to be h. So of course there has to be an equilibrium, and I'm not drawing everything because this would not make it equilibrium. It would not make it static because there would be this direction of movement basically because of it. But we do have it, but I'm just not drawing everything. And then we're also thinking about some idea of some force that would combine the two, calling it W. And this force is basically the main part of the idea. In this case, it has to be under an angle that's not natural. It's not like a perpendicular angle or parallel to the horizontal plane. But in the case when we're going to be considering the idea of an inclined plane and an object on that, it will actually be at the place of the weight force directly. So the m times g will be this one, and these ones will be like kind of the ones that are at an angle related to the reference frame from which we naturally view it. But in any case, this W here has some relation, namely we will find the angle between n and W. I'll call it theta. And then we can have a tangent of theta by trig function definitions. Well, we'll have h over n. equaling to tangent of theta. And let's at this point define the point in time when we get to the point where very small increment in force will a very small outer force will cause the body to start moving. And that happens when the normal force times the static friction coefficient equals to the horizontal force. So this horizontal force directly equal to the normal force times what is the coefficient. And by that definition, we have that by this definition, I can actually put it here now. Because what I'm talking about here is some angle. So if I replace this N and H by some other force, basically impacting this thing under an angle, it will say that what angle does it have to have for this to start moving? Well, I will rewrite this. I will write the H because of this equation. N times mu sub s over n. And the only thing that will remain is mu sub s. So tangent of theta of this angle right here will be this static coefficient of friction. And so that says that if we have this W kind of resultant force, the angle at which is with the perpendicular normal force is going to be the arctangent or inverse tangent of the static coefficient of friction, which is interesting. So theta will be the inverse tangent of the static coefficient of friction. So that is interesting to see. So from this perspective, we have this kind of scenario, and that basically tells us that if V is inside the range of this theta, of this max theta, because what I defined is this is equal, so this is the very point where it will start moving, just some outer force in the direction of desired motion that it's tending to, that is kind of seeming to start going in, some extra push, and it will start moving. And of course, by the way, the friction coefficient will switch from the static one, which is usually higher than the kinematic one, to the kinematic one. And that kinetic coefficient of friction is usually lower for most cases, for most materials. Alright, so we have this kind of out of the way, and that is the point. So we're looking, so as long as this W is inside the theta, it will stay static. But once the W goes kind of beyond it, this angle gets bigger than this theta, which is like kind of a limiting angle, then surely the free body will not stay static and it will start moving. So that's the point here. So when it's surpassed, then that happens. And it's also interesting to see that this angle is directly related to the coefficient of static friction. Also because the coefficient of static friction is precisely defined as, if it's now equal, then for that scenario, for that transition point between static friction and kinetic friction, the friction that applies when it's still static versus the friction that applies when it's moving, well, for that point, this equation applies, and thereby it also applies that the horizontal is, by the way, the friction force, I can say, and the N is, that normal force caused by some gravity or something, making the body like connected to the surface like that, or be on the surface. So the precise ratio between them is the static coefficient of friction. So when that happens, we have this identity, and this thing can be further developed in the context of an inclined plane, because basically the idea will be the same. The idea will be the same because we can draw a very similar thing in that context. What we will have is something in this sense. So one can have an inclined plane and the body will be on that inclined plane. And so there is some weight force, in this case the normal force, let's say that is and now I'll draw it actually going down. Again, if I'm saying this is still static, then there has to be an equilibrium and there should be more forces drawn. But let's just do it the simple way. Let's just draw what we're looking at, what matters most. mg going down, that's the weight force, mass times gravity, gravitational acceleration, whatever that is. And then if I have some two forces, one in the direction of, let's say, so actually, if I want to talk again, I want to not do the motion force, the force that causes it, because that will be basically a projection along some axis parallel to the surface of this inclined line. But let's talk about that. I'll do a force that causes it to stay static, or kind of the friction force. Again, call it perhaps H. And then I also have a normal force. So let's say again M. And so how do we get these two? Well, again I will consider some angle, and the angle that I precisely consider will be this angle. By geometric identities, turns out that this angle, so basically what we're talking about is we have a inclined plane underneath is this free body, and we want to see what has to be the angle in order for this free body to start sliding down by itself. Actually, this angle is also here if we draw out the force components. And although here it's not drawn with the correct scaling and so on, by this angle I can already relate to the mg and mh, both of them. So, namely, n will be if this is theta, then this should be n should be cosine, so mg times cosine of the theta. And h then should be well, it's drawn like this, but it could also be drawn like this. We could create this parallelogram to denote graphically how it's derived. So basically, for the horizontal component of it, it will be the cosine, and this will be the sine. So h should be mg times sine of the theta. And now again, I can draw that equation when, if I had said that for that very moment between it's still static and it will start moving very soon, it is the static coefficient of friction times n equals the horizontal, let's say, friction force, then again, as before, is the same thing. H over n equals that coefficient of friction, the static one. And in this case, we can again derive the tangent, but in this case it's even more straightforward perhaps. Well, we had realized the cosine and sine before, so it might have not been as straightforward, but this part is more straightforward because we don't have to realize the tangent so graphically now. H and n are this, so I can write it there. So it's mg sine theta over mg cosine theta, substituting for h and n, and that ends up being the tangent of theta. So in the end, we again get that the static coefficient of friction is tangent of theta. And again, from this, the theta will be the arc tangent, could write arc tangent also like this, of static coefficient of friction. So, we see that regardless of the actual weight and gravitational acceleration, because that's kind of been cancelled out here, we can directly relate the angle at which it will start sliding to the ratio between the two components. And so that's an interesting thing to keep in mind, or to see that if we have these parallel components, one is the horizontal thing as a result of friction, and then of course the friction force is directly reliant on the coefficient of friction and the normal force, their product. Then the ratio of these two, the quotient of these two, will give the coefficient of friction back, and then the angle at which we need to have this free body for it to start sliding. Well, it has to be. This is the angle at which there's this switch. So intuitively already, once it's a little higher than theta, definitely it will start sliding down. If it's lower, then it will just stay in place.